Okay, so let's go ahead. We're going to start with chapter 14, which is partial differentiation. And 14.1 is just kind of is an introduction to functions of several variables. And so, what? So, okay, on the homework, how's that? Okay, this thing's going wacko. Okay, so, okay, there we go. I think it's better. Okay, so, and just as an introduction, here's an example. So this is the function, right? This is exercise number 1. So we have I is equal to f of th. So I is the apparent temperature. Okay, so I, in this case, represents the apparent temperature. So what that means is, the actual temperature could be 90 degrees. Okay, but if there is 50% humidity, then it feels like 96 degrees. Okay, so that's the apparent temperature. It feels like 96. It's only 90, but because of humidity, it feels like 96. Or it's only 90, and because of 70% humidity, it feels like 106. Okay, whereas if there's only 20% humidity, it will only feel like 87. That's according to this chart here. So the actual apparent temperature, what it feels like, is a function of the actual temperature and the humidity. Okay, so that's a function of 2 variables. When you say it's a function of several variables, that means more than 1 variable. So here we have 2 variables. There's 2 independent variables, and I is the dependent variable. Okay, so part A. What's the value of f of 9570? And what does it mean? Does anybody want to take a crack at that? What's f of 9570? We're looking for a number here.
Is it 124?
Yes, it's 124. It's this one here. Wait, this one here. Okay, because here's 95 and here's 70. So it's 124. Okay, so which means that the actual temperature is 95 degrees. That when the actual temperature is 95 degrees and the relative humidity is 70%, the perceived air temperature is approximately 124 degrees. Okay. So I believe that's the answer to part A. Okay, so for part B, for what value of H is f of 80 comma H equal to 82? Okay, so we're talking right here. Okay, so anybody want to give an answer to that? For what value of T is, wait, I'm sorry. For what value of H is f of 80H equal to 82?
$60.
Yeah, that's going to be 60 because there's the 82 and there's the, so it's going to be 60. 60 gives you the 82. Okay, and then the last one, or part C, I'm sorry, not the last one. What value of T is f of T 40 equal to 93?
90.
90? Yes. Yeah. So this is going to be 90 because when you have a 40, that gives you 93, right? So 90 will be the answer. And then the last part, what are the meanings of the functions? Okay, so this is, I think the only reason I put this question on the homework is because of this part D right here. What are the meanings of the functions I equals f of 85 comma H? So if you, so here's the 85 right here. So this line right here, so this whole line right here represents a single variable function, okay? Because if you fix 85, then you have like a single variable. So this could be thought of as like g of h. Okay, so it's only a function of humidity, given that the temperature is, but the temperature is fixed at 85, and then this is just a function. So these values right here are what happens when you're 85 degrees. And so that's a one variable function. Okay, not two variables, but just one variable. So the only variable is h because you've already fixed the temperature to T. Okay, so that's the idea there. These are one variable functions now. It's like kind of what we're used to. And then let's see the other. So I of equals means that T is fixed at 85 and H is allowed to vary. Then the actual temperature is 85. Similarly, I is a function of one variable constant humidity value for different relative humidities when the actual temperature is 100. Looking at the rows of the table corresponding, we see that H of 85, H is what?
It increases.
Yes, it increases. And so it increases. Okay, then, so why does it increase? Let's see, 85 and 100. So 85, as you're going across with 2, increase by 2, increase by 2, 2, 2, and then increases by 3 there, right? Well, f of 100h, that increases by 5, and then by 6, and then by 10, and then by 12, and then from 132, that's another 12 right there. So this f of 108 also increases more quickly. At first with an average of 5 degrees and at an increasing rate, right? So not only is the actual number increasing, but the rate at which it's increasing is also increasing. Which means concave up, right? That's the second derivative. Okay. Okay, so that's number 1. Let's go to number 2. And let's see. Number 2 says we have this function here. The manufacturer has modeled its yearly production function P, the monetary value of its entire production in millions of dollars, as a Cobb-Douglas function, whatever that is. And here's the formula right here. 1.47 L to the 0.65 times K to the 0.35, where L is the number of labor hours and K is the invested capital in millions of dollars. Find P of 135.60 and interpret it. Okay, so that would be, you take 1.47 and then for L gets replaced with 135. And then K gets replaced with 60. Okay, so then we grab our calculator and plug those numbers in. Let me know when you guys get an answer, okay? Okay, I got 149.4.
I got the same thing.
Okay, well, let's see if Webassign agrees. Or do we have to go beat him up or something? Okay, I'm glad for Webassign's sake that they agreed. Okay, so the manufacturing, okay, so then it says, so when the manufacturer invests 135 million, so this is, L is the No, L is like, oh, wait. I should have known. Okay, so the K stands for capital. And L stands for labor. Okay, so when the manufacturer invests 60 million, that's the next answer, in capital and 135,000 hours in labor completed yearly, the monetary value of the production is this. Okay, so this, so the next question would be, the answers are 60, 135, and 149.4. Okay. Okay, so that one, and that one. For the second part. And for the first part, it's just this. Okay, so that's number 2. Number 3, evaluate. Okay, so here we have g of xy is cosine of x plus 5y. Evaluate g of 10 comma negative 2. Okay, so that's going to be, you're replacing, so it's x's first, then y. So replacing all the x's with 10s, and replacing all the y's with 2s, which really works out nice here because then you just get 0, right? Yay, cosine of 0. What's cosine of 0?
1.
Yes. That's also uno in Spanish, by the way.
Uno.
I'm teaching Spanish too. Okay, so that's 1 is the first answer. Okay, part B, find the domain of G. Okay, now you can put anything in for x and y, right? Because cosine, it can take negative values, it can take positive values. You can put any real numbers in for x and y. Okay, so you can kind of think of, so you're thinking, okay, so x can range from negative infinity to infinity, and y can range from negative infinity to infinity, right? And when that happens, the way that you express it is like this. So this r right here that has this line like that, that counts for the real numbers. But if you put a 2 here, you'd raise it to the second power, then that's the whole Cartesian plane. If you raise it to 3, then that's x, y, and z. Okay. If you raise it to 4, then that's 4 dimensions, and so on. Okay. So here it's our, right. So that's the answer. Then that's part B. Part C is find the range. Okay. Now, most of the functions that we're dealing with the functions that we're dealing with, there's 2 variables, right? There's 2 variables there, 2 independent variables. Here, there's 2 independent variables. However, when you plug it into here, you're going to get just a real number, okay? And since it's cosine, that real number is going to be between what and what? Cosine can only take on values between negative
1.
1 and 1, yeah. Between negative 1 and 1. Those are the only values that the cosine can take on. Now, so here, for both of these functions, so here you have the p. And for real valued, for multiple valued functions, functions of several variables, it's important to kind of realize what you're dealing with. Okay, so this one right here takes real R2 to R. And here, this G also does that. Oops. And that's how I write this, okay? So here you're taking, there's 2 input variables which means it's R2. And then they get taken to a single value, which is R. Okay, now we will have functions that will do stuff like R3 to R. We will have functions that are doing stuff like R2 to R2. And that starts getting really weird or complicated. And maybe R3 to R3 or R5 to R2 or 5 to 7. And so different things like that. So there's functions that instead of just giving you back one value, it gives you back, a number of values. And so it's kind of important to realize what you're dealing with, okay? Okay, so moving along, number 4. We're supposed to find and sketch the domain of this function. Okay, so here again, there's 2 input variables. So you're looking at this. Okay, but it's the logarithm. What restrictions are there on putting values in the logarithm? Does anybody remember?
It can't be negative, correct?
Right. It can't be negative. It can't be 0 either.
Right.
So that means it has to be greater than 0. Okay. So it has to be like that. Okay. So now that's what the domain's going to look like. So the domain's going to be everything that satisfies these conditions. And if you take all this to the side, they become positive, right? And then we're just going to it's going to be like that in actuality, which is, which I guess you could rewrite it like this if you wanted. Wait, that's squared.
Is that in the equation of a circle?
No, there's a couple of problems with it. What are the, to be in a circle, it has to be x squared plus y squared. And it can't have like one of them divided by 25 and another not. So it's not a circle. Okay, and then also this is like an inequality. But what is this the graph of? Does anybody remember? Oops, 25, 52. What's this the graph of? Does
Hyperbola.
anybody remember?
An ellipse.
Oh wait, you know what? I can't believe it. Gremlin struck again. Okay, that's an ellipse, right?
Yes.
And you're going to go out by 25 on the x-axis and up and down 1 on the y-axis, right? Not 25, 5. It'll go out by 5 on that. So it's going to look like this. This is going to be the boundary of your thing. And this right here means it's going to be the inside. Because less than means that you're going to be, your set is going to be the inside of this. Okay, so in the pictures, it's going to be the bottom right picture. Okay, great. So let's look at the next one, number 5. And we're supposed to find and sketch the domain of this. Okay, so where does the square root have problems? What numbers can you take the square root of? Or what numbers can you not take the square root of?
0. Infinity.
Infinity. Nah,
Or
did you say negative?
Negative numbers. That's what I said.
Yeah. You don't take the square root of negative numbers in this class because this is a real numbers class, right? So, you can take the square root of 0 though. So that's greater. So greater than or equal to 0 is what you need. And that turns out to be that. Okay. So that part is just hyperbola. And so if it's just that, so there's that looking like that. And it's going to be this part up here, right? That's what this is. Okay. But then the denominator splits up into this 7 minus x and 7 plus x. Okay. And then these two factors are in the denominator. And what does that mean? This means x can't be 7, right? Because that would make the denominator 0.
So those are your new limits then?
These are restrictions that you can't have. So if that's 7 and that's negative 7, then you have to like knock out all this part here and have to knock out all that there. Okay. So it looks like the bottom left is the answer. Okay, good. Let's move on to number 6. Sketch the graph of this. Okay, so here, to sketch the graph, you look at it this way. You sketch the graph of that. So you have the x, so you have the x, y, and the z plane over here. No, I mean x, y, and z axes. Oops. And you're gonna plot points, okay? So the easiest thing to do is to see what happens if you set so like let's say so for example, let's say we want to find out where it intersects the or first of all, let me ask this. What do you think? What kind of object do you think this is going to be?
An egg shape.
A what?
An egg shape.
An orb shape?
Oh, I don't know. I was just looking at the. I said circle.
Yeah, I wanted it to be an orb shape too. That sounds fun. What?
More like a pyramid, a triangle.
Okay, so you have the 4 things. You have the 4 shapes here. One of them looks like this orb shape, a circle, a disc, and a sphere, and then looks like a basketball. Oh, let's go play some basketball. And then no, can't do it. And then a pyramid. Interesting. But okay, so ignore their shapes though, because they're all misleading. I can tell you right now, they're all misleading. Every single one of those shapes is misleading, you guys. I can't believe it. Wow.
Well, Brother Hirsch, you're the one who started the shaping.
but then again, one of those somehow has to be right? Whoa. Okay, so
This is right.
Do that. Okay, do this. Okay, so do this. So if you bring these guys over to the left, and you get this. Okay, so now, just look at this equation here. What is this the equation of? Come on, did the test fry your brain?
Yeah.
This was on the test. That's a plane, yes.
Haha.
Yeah, okay. Yes, that's a plane. Okay, so like, yes. Right? And the normal to the plane is 451, right? 451 is the normal to the plane. That's a plane. Okay. So, what you're going to look for is, where does the plane intersect the x-axis? We'll call it the x-axis intercept.
Well, you just have to solve for x, don't you?
Yeah. So you set
Is it
y.
Y?
You set y and z are both equal to 0, and then x is going to be 18 over 4, which is 9 halves. So it's going to intersect here at 9 halves. And then the y-axis, you're going to set x and z equal to 0, and it's going to intersect. It's going to be 5y equals 18. So y is 18 over 5. So that's going to be 18 over 5. And then the z-axis, that's going to be where z is 18. So it's going to be 18, right? Up here. It's going to intersect at those 3 places. Okay, and now it's going to look at, it's going to be a plane that intersects like that, but then continues going out in all directions, right? But, so the answer is that it's actually the pyramid shaped thing. Well, it looks like a pyramid, but it's actually just a plane.
So it's not a pyramid, but a plane.
Yeah, so because it keeps going out in all directions. So this is one way to typically draw a plane, but in reality, it keeps on going out in all these directions.
Mm.
It just keeps going out. It just keeps going out. So it's all the way over here and over there. It just goes everywhere. Well, not everywhere.
There's just no shape.
Yeah, it's just a plane, like if you're extended tabletop or something. Okay, so number 7. More adventures in graphing, sketching graphs. Okay, so here we have z. What? Z equals sine x. Okay, so now the thing is, you're like, whoa, this is a function in 2 variables, really? But there's only 1 variable here. So you're like, oh, but Brother Hirsch copied that down right. Did Webassign copy that down right? Why isn't there another y right there? If it's a function in x and y, why isn't there a y? And the thing is, it doesn't really matter. It doesn't, I guess you don't need to have a y there for it to do something.
Hey, Taylor, your mic is on.
My bad.
Okay, so let's do the axis right here. So there's no y in the expression, but it can still be a function of y, even though there's no y in the expression. Somehow it's able to achieve that. If we were to just go, okay, if we were just to say, well, let's have x and z. Okay, so this would be like the sign, but here's z instead of y, right? Because that z, there's a z here instead of a y. But if this were a y and that were a y, then what would the sine function look like? I guess it's kind of hard to describe, right?
It would
It's
just
going to
be
go
like
through
a
the origin.
wave.
Yeah, it's just this wave right here that comes up here, and at pi it crosses over and then goes under, and so on. It just keeps doing that, and then goes back this way. Now, so that would kind of come up here, and then go under. Because this part right here would be like this part there, and this part going under would be kind of like this part here. And so on like that, right? And then back going that way, it's gonna like do the same thing as it goes back this way, and so on, right? Okay, so now, but the thing is, it's going to do that over here too. That's going to come. So it's going to come. So right here, if you come over here, there's going to be. So this is like. This is through the. This is along the x-axis. But if you were to come out here, then it would be parallel to that because it doesn't. Okay. So you'd have like this. This might be like this corrugated. Rooftop or something. Corrugated roofing. Okay, like this. And so which of these sketches does it look like it is? Well,
Looks like
all
it
the
could be
sketches
either
are
the
like,
top left or the bottom right.
yeah, it looks like the top, wait, top.
Oh, but it could be the other one too. What the heck?
But
No,
sometimes
wait.
I tell you though, your microphone is just kind of messed up, or maybe my speaker's messed up. Okay, it looks like to me it's going to be the top right. That looks like me because this is the positive direction on the x-axis over here. This is the positive direction. So it's going to come out like that. It's going to go up like that. So here, and the bottom left, it looks like it goes up and then it dips down a lot further than it should. The bottom left one does, and then the other two are doing waves along the y. Okay. Where it should be, if you go along, if you take a point on this and you go up and out and you go parallel to the y-axis, then it's just going to be a straight line. So it is the upper right. Okay. Okay, great. So that one there. Now, number 8. Okay, so here I have a contour map of which is shown. Use it to make a rough sketch of the graph of f. So this is a contour map. What this means is that along this line right here, so you'll notice that you have the z's coming up and the x's and y's, right? And you basically have z is a function of x and y, is what it is. Okay, so this xy here, this xy plane right here represents the, or you could think of the xy plane as being the domain. Okay, so think of it that way. So the domain is equal to the xy plane. And, okay, so in the regular graph, just suppose it's a regular graph, your domain is this x-axis, right? And your range is the y-axis. Okay, but here the domain is the whole xy plane, and the range is going up or down. And what this 0 means is that everywhere along this line, the function is 0. Okay, so everywhere along that line, the graph is going to be 0. So this is the correspond to that line. Okay. So everywhere along that line, as you come straight out, the function has to be 0 right there. Okay, and it's only this function that does that, because this is like this is like it's kind of going down like that. This one is just going up, and then this one, as you come out here, it's just like coming down. It's just up here. It's on the slope here. Okay, so but along this line, you're 0. Now, along this curve right here, your function is equal to 1. And also along here, along this curve, the function is 1. Okay, so that would be like Whoa, this is kind of hard. So that'd be like going here, something like this, you know. Your function's got to be 1 along there, and it does seem to be that case because look, this is kind of up by, it's kind of up by 1 along on that little part right there, and the same thing over here. Around here, it's going to be 1, which it looks like it is, because up here it's 1. So this has got to be the answer right here, as far as I can tell. Okay, so that's what contour maps are, and then like if you're familiar with reading maps, then that's what it is. You'll see like contour lines, which tells you the elevation. And you can kind of tell from this where the graph is going is really steep and where it's not so steep. So like, for example, right here, where the contour lines are close together, the graph's really steep. But when they're further apart, like right here, from here to here, it's not as steep as say, but as you go up, it's getting steeper and steeper and steeper because you know these are getting closer and closer together, right? And same thing over here. And maybe this is not a really good example for that, but when so that's how that works. Okay, so now let's see, number 9. Draw a contour map of the function showing several level curves. Now, contour lines, these contours right here, these are called level curves. So maybe I should introduce that right here. Level curves. So what happens there is you choose a value. Okay, so for example, let's say we choose the value 1 or 0. I'm sorry. Let's say we choose 0. Okay, then f of xy equals 0 is a level curve, and that would be this line right here. That would be this one right here. It'd be that level curve. Okay, and then if you were to choose let's say we choose 1. That's going to be another level curve. It would be f of xy equals 1. Okay, and that's going to be these curves here, this one and this one. Those are level curves for choosing 1. And then if you choose 2, everything at height 2, that's a level curve, and that's a level curve. Okay, so the level curves are in the xy plane. Okay, so these are in the xy plane. And they're a way to help us understand what the function looks like. Okay, so their purpose is to help us understand what the function looks like. Okay, so here's an example. So this is like z equals, to graph this, so we'd have to graph this, right? Which would be 3 dimensions. So you would have to have a z-axis and the y-axis and the x-axis. You'd have to graph it like that, right? And it becomes some kind of a surface in this. Was what the graph would look like. But what they want us to do is graph level curves. Okay, so you start with like maybe, let's say we start with 0. And so we're going to look at f of xy equals 0. That means you're going to place you're going to take x squared minus y squared equals 0. Or which is the same as y squared equals x squared. And this also is y could be x or y could be negative x to satisfy this, right? So there's 2 ways to satisfy this, y equals x and y equals negative x. And so can you see one of these graphs here that has these 2 curves on it, y equals x and y equals negative x? There's only one of them that does. So which one is it?
It's the top right.
Yeah, it's this one right here. So this is y equals x. This is y equals negative x. Okay. Now it doesn't say, well, I think that kind of rules out the other ones because there's no way that you can get those in there without without crossing over other level curves. I mean, because there could be level curves that are not shown here, right? And so like if we had gotten, let's say if we gotten a circle here that's smaller, that's just smaller than that circle, it's right here, then that doesn't rule out this one as a possibility. But if you have stuff that goes through like that, then there's no way, because this is saying this number is different than that, this value is different than that value, and so on. But they all should be the same in order for there to be a level curve right there. The same thing there, same thing there. So there's different values that it's crossing through. So these three can't be the answer. Okay, they can't be the answer. This is the only possible answer. And we could also do other curves. So like, let's say we chose we chose 1 instead of 0. Okay, then we would set this equal to 1. And that would be a hyperbola, right? That would be, let me see here. That would be this hyperbola here, right? And that one. Oops. Okay. And then if we set if we took -1, so that would be x squared minus y squared equals -1, which would be the same as y squared minus x squared equals 1. And that would be these two curves here, maybe. So that would be another, so this is a hyperbola going this way. And then this one's a hyperbola going this way. And so these are all different. So these are all different level curves. This would be the one corresponding to 1. Okay, this would correspond to 0. And perhaps this would correspond to -1. Okay, and -1 here also. Okay, so something like that. So that's what level curves are about. It helps us understand what the graph's going to look like. On a map, it helps you understand what the altitude is. And again, where you have level curves that are close to each other, that means you're either going up or down more rapidly than if they're spaced further apart. Okay, now, if we take it up a notch, so we're adding another variable here. So this is a function of 3 variables. Okay, so here we have something new, which wasn't the previous one. You're taking 3 variables to 1 variable. Okay, and so so to graph it, we would have to look at it something like this. W equals x squared plus 5 y squared plus 5z squared. Like that. And again, over here, to graph this one, which is a function of 2 variables. Okay, so this is going from, this f is going from R2 to R. Its graph is going to be in space, right there. Its graph's going to be in space. Now, if we go R3 to R, then you can't really graph that because, you know, what do you do? How do you graph it? Because its graph is like, those are 3 variables. It's like 4, you need 4, you need like a 4 space. We don't have 4 space, or we can't visualize the 4 space. Okay, or maybe it would be like, maybe we need some flashcards, and the 4th space could be the time dimension where you're flashing through the cards for different values of W. Okay, what it looks like. But what we can do is over here, because in this one, the level curves are in 2-space, or just 2-dimensional in the Cartesian plane, then for this one, the level, it's going to be level surfaces instead of level curves. Okay, so it's going to be level surfaces. And those are going to be in 3-dimensional space. So we're good there. So now, so what we're going to do is to get level surfaces, you just set these equal to constants. Okay, and what does this look like the graph of? Wait, 10 is just a multiple choice question? Ooh.
Isn't that an ellipse again?
Yes. Well, ellipsoid, because ellipse would be 2-dimensional, but this is ellipsoid. Okay, so if we were to say, like just for example, if we were to choose, let's say we choose C to be 5, for example. You don't have to choose it to be 5, but let's just suppose that we had chosen it to be 5. I guess that would be like the easiest choice, because they can divide everything by 5. Wait, this is squared. You have a 1 over there. That means it's going to go out along the x-axis. It's going to go out and back by the square root of 5. And then because these are both divided by 1, then it's just going to go 1 up and down there, and the y along the y and z axis. Okay. So I'm not going to try to draw it. If you were to choose like C equal to, you could also choose C to be equal to 1. Okay. Then it would be x squared plus, you could rewrite this as y squared, it's all equal to 1. Y squared over 1 over, you could like write it like that, which is really weird. Okay, so if you're choosing C equal to 1, then 5 is the same as 1 over the square root of 5 all squared. So it's going to be out and back. It's going to go through on the y-axis. It's going to go through 1 over root 5 and negative 1 over root 5, and then on the z-axis, it's going to go through 1 over root 5 and negative 1 over 5. On the x-axis, it's going to go through 1 and negative 1. Okay. And then if you were to choose C equal to 0, then you would get this. And that would just be the point. That's the only thing that it satisfies. And if you choose C equal to -1, that would be the empty set. So nothing would happen there, because you can't have them adding up to a negative number. Okay, so ellipsoids is what they're going to be like. Well, in conception, one of them is going to be a point, and then some of them are non-existent, but in general, it's going to be ellipsoid. Okay. Wow, we made it through everything.